In anything we do, in significance testing, there can be errors, and sometimes we will be wrong. And they're very similar to the errors like a jury could make when in a trial. One, they may say they are guilty when really they were not guilty. And they can say they were not guilty when really they were. Okay? For us, that translates into rejecting and not rejecting the null. In a significance test, an error that we can make is that we can reject the null when we should have failed to reject. And we can fail to reject the null when we should have rejected. Okay, these have two very specific names. You can remember the names, but if you're going to, make sure you get the names right. This one right here, rejecting when you should have failed to reject, it's called a type 1 error. Now, I would rather you say, and so would the AP readers, that like explain the error. Oh, the error is that I should have rejected the null, or I rejected the null, but I should have failed to reject. Rather than say type 1 error and mix up the two types. This one, fail to reject, is a type 2 error. So their names are very similar, type 1 and type 2. It's much better to just explain the error. Oh, I failed to reject the null, but I should have rejected it. That's a type 2 error. But if you explain it out in words, you're going to get the same credit as if you said type 2 error. Okay, so there's 4 different combination of ways in which a solution to a significance test can happen. And you can think about it almost like making a Punnett square. Okay, if this is the truth, these are my options for the truth, and these are the conclusions that we made based on the test and the sample. Okay, I can either know that the null is true or the null is false, which would make the alternative true. Okay, and here we can either conclude to reject the null or fail to reject the null. Okay, if I reject the null but the null was really true, that's where that type 1 error comes in, because I failed to reject, or I rejected when I should have failed to reject. Okay, but if I rejected and it was false, then that means I got it right. Likewise, if I failed to reject it and it really is true, that means I got it right. But if I failed to reject it and it really was false, then that's where the type 2 error comes in. Okay, there was a question on the previous page about which one is worse. Okay, it really depends on the situations. Different errors result in different problems, and so it depends on the situation which one is worse. So let's look at this example and talk about which one of these might be worse. The manager of a fast food restaurant wants to reduce the proportion of drive-thru customers who have to wait more than 2 minutes to receive their food once their order is placed. So based on the store records, the proportion of customers who had to wait at least 2 minutes was 0.63. Okay. To reduce this, the manager assigns an additional employee to assist with drive-thru orders, and during the next month, he collects a random sample of drive-thru times and tests the following hypothesis. Here's our null, which remember is a statement of no difference, which is why this is the same as it was before. And he wants the proportion to become less. Okay, he wants it to be less than 0.63 because he wants fewer customers to have to wait that long. Okay, so what are our type 1 and 2 errors? Well, our type 1 error would be that we reject the null and say the proportion is smaller than it was. help if I could spell proportion. Okay. The proportion of customers who have to wait has decreased when really it hasn't. So what would be a consequence of this? Hopefully you're thinking that something along the lines of, well, he thinks that the drive-through times have gone down when really they haven't, so he thinks his solution's working and he keeps, employing this person to help with the drive-through when really it hasn't helped. Or he still has customers who are upset because they have to wait so long. Okay, there's a number of different consequences of this. He stops thinking of a new way to decrease these times because he thinks he has one that works when really he doesn't. Okay, and a type 2 error would be the opposite. He thinks it has not. He thinks the times have not decreased when really they have. And the consequences of this would be he thinks that extra drive-through employee is not helping, so he takes them away when really they were helping. So, things like that. Okay, you may be thinking, well, what does this even have to do with anything? Because wouldn't he know? Okay, wouldn't he look at his results and know whether or not the times would decrease? So why is he having to guess, and why wouldn't he have these errors? Remember, he is only working with a random sample. So depending on the data he gets from his sample, it's not going to be from every drive-through customer that comes through. So he may, just by random chance, get all really high values, and maybe they all are more than 2 minutes. Or maybe he gets really low values, and they're all below 2 minutes. Or maybe they're spread equally out, and he can see. It depends on the sample he takes, because we all know that samples vary from sample to sample. So he may, depending on the sample data he gets, it may lead him to one conclusion versus the other, which is why the errors come in, because we're working with just sample data. Okay, so a check your understanding time on page 539. So pause the video, look at the problems, check your understanding, and then restart it so you can check your answers. Okay, hopefully you have restarted the video. When all the answers come up, you can pause it and look at them and check your answers. Okay, so let's talk about the probability of a type 1 error. If you think about it, we have our sampling distribution, our normal curve, and we have all the different values of, well, if we're going to stick with our McDonald's or fast food or whatever fast food chain you want to think about it, those were p-hats. So we have all the different values of p-hats that we could possibly get, all in this normal distribution. And where we get our p-value, remember, is that we set some alpha value. And alpha typically could be set to 0.05, which means that all of this in here is 5% of the possible p-hats. So if our values are 5% of the top 5% or the bottom 5%, depending on the direction, then that's our probability. So our probability of a type 1 error, because if I'm wrong, I still have a 5% chance of picking one of those values, is the value of alpha. The probability that a type 1 error is going to occur is whatever your alpha value is. Okay, and if you want to reduce the probability of a type 1 error, you can do a couple things, and the main one is to reduce your value of alpha. Okay, so one thing that you want to make sure that you think of when you are deciding on your significance level is, how much of a probability would you like of a type 1 error? Is it a big deal to you if you were wrong, if you reject it when you really shouldn't have? Because if it is, then you probably want to reduce alpha and make it smaller than what it actually is. Okay? Are there drawbacks to this? Yes, there are. If you mess with the value of alpha, if you reduce it, while your probability of committing an error is going to be less, so is the probability of rejecting the null. So if it really is false, if you really should reject it, you're going to have a lower probability of accurately doing so because you're trying to reduce the fact that you might make an error. Okay, a type 1 error is represented as alpha. A type 2 error we represent as beta. However, we don't really talk about type 2 errors as much as we talk about the power of a test. They are closely related, type 2 and power, and in fact, power is 1 minus beta, which is the probability of a type 2 error. And so you might ask, what is power? How do I calculate it? Well, the good thing to know is that you will not be expected to calculate power on the AP exam. What you were going to be expected to be able to do is to talk about it. Okay, to understand how power is calculated and the general idea behind power, which is this. Let's say we have a normal curve. Okay, and here is our alpha value, which means that anything on this side is going to cause me to reject, and anything on this side is going to cause me to fail to reject. And I'm just going to call that FTR, fail to reject. Okay, here I'm going to reject the null. This side I would fail to reject the null. Okay, and whatever this probability is here, whatever this alpha value is, that's equal to the probability of a type 1 error. Okay, to calculate the power, we say this, and you calculate the power at specific values. We say, okay, what is the likelihood that I am going to detect something is wrong if I really am supposed to reject the null? So I say that, okay, let's say my true value is, let's say that this true mean right here was 0.08, and that way out here somewhere is 0.11. Okay? Let's say, alright, what is the probability that I would detect an error if my true value was really 0.11? So if my true value was really 0.11, then 0.11 would be at the center of my curve, and my rejection line, instead of being at the very end, would be here. And that means that all of this would actually get rejected. So even though it doesn't seem like I'm rejecting much here, if in fact my true p-value, if my null was wrong and my true p-value really was 0.11, then in reality, all of this, okay, more than half of my possible responses would enable me to reject. And I actually would look at this probability, and this probability right here is my power. Whatever that probability is, that area under the curve. And this area over here would be my probability of a type 2 error, or my beta. Okay, these values are going to be different if I'm assuming a different value. So if I'm assuming that my alpha, or if I'm assuming my true mean really is smaller than 0.08, if I assume it's like 0.07, then my power for this test would be really small because I would scoot this over and much less of my curve would be covered. Or if I assumed it was 0.12, then that means more of my test would be covered. Okay, so when thinking about planning your study, it's important to think about power and to know a couple things about power. And just kind of keeping this in mind is all you'll really need to know for the AP test. You need to know for the AP test that power is 1 minus the probability of a type 2 error, and that you do it for specific values, and that there are 4 factors that affect the power of a test. There are 3 factors that affect the power of a test. One is the significance level. Because obviously, if you think about our picture we just draw, if my significance level is different, then that line would be at a different place. So if my significance level was really 0.1, it would be more to this side, which means even more, my power would be even higher. So a higher significance level, okay, a larger significance level produces a larger power. 2, you want to think about the practical importance. Okay, how large a difference between your hypothesized value and the actual one is really important. And it depends on the scenario and on the field of study that you're in. Some fields may need even the smallest difference may be important, and in some you may have a few percentage points before it really becomes a big deal. And 3, you want to think about when you're planning your study, how confident do you want to be? How confident do you want to be that your study will detect a difference between certain values? So, is it important that I pick up on the difference between 0.08 and 0.09? Or is from 0.08 to 0.11 good enough? So, how confident do I want to be? Okay, here's a couple of other things to remember. If you really want a good power, if you choose a smaller significance level, like 1% instead of 5%, then you need to take larger samples. Okay? Smaller alphas need larger n's. Okay? If you really want a high power, okay, so that means if you really want to be confident, because confidence is basically power. If you really want a high confidence, so a high power, you need a larger n. Okay? And in any difference, okay, any significance level, if I want small differences to be detected, if I want to be able to pick up the difference between 0.08 and 0.09 versus 0.08 and 0.11, I need a larger sample size. You will never go wrong with having a larger sample size.